In this video I'm going to go through a whole bunch of HSC E equals FLeA questions. So when we have this formula E equals FLeA, we know that E is the Young's modulus of elasticity, which is equal to stress over strain. If we know that stress equals force over area, and we know that strain equals change in length divided by original length, better written as E over L, what we get is, we get this formula where we have which gets us to, as Flynn has written so nicely on the board for me, E equals FLeA. Now it's important to remember that there's lots of different ways that we can rewrite this. We can write E equals FLeA. I love that symmetry, that you can swap either of the E's. The A can be swapped nicely as well, so you can say A equals FLeA, right? And then the other ones, they get a little bit messy. So F equals EEA over L, and L equals EEA over F. I will be honest, I don't remember these ones, but that's algebra, that seems right. Yep. Okay, great. So sometimes we will need to rearrange those formulas, but this E equals FLeA formula will not be given in the exam. This will be given, and this will be given. Right? So those three formulas will be given on the formula sheet. From that you have to derive E equals FLeA. So what we're going to do is we're going to go through a whole bunch of past HSC questions. Could you get the projector working? We're going to start with a question from 2002, question 12. Okay, not the neatest handwriting I've ever had in my life. Okay, so it says, I'm going to read out the question. I'm keeping that in there. Okay, so I'm going to read out the question, and I might actually get someone else to read out the question, and then I will write what the pertinent facts as we go. So, can you read that off? So, a diameter 10 cable
is attached to the truss.
Yep.
To support the electricity supply. The doctor has shown the material currently used for the support cable has Young's modulus of 180 GPa.
Yep.
And must withstand a maximum tensile force of 6 kilonewtons.
Okay, so the force is 6,000 newtons. Now you'll notice that I've converted gigapascals into 1,000 megapascals. And that's because of Greece units. We go together like megapascals and millimeters squared. Okay, they have actually given us E equals FLeA in this question. Now it's on the formula sheet, but it is listed on the question itself. I've written newtons because we always use newtons. Occasionally we use kilonewton meters, but we really want to just be using newtons. Okay, so the thing is, there's no diameter in this question. So what we need to do is we need to find the area. So area equals pi d squared on 4. If you want to use something to do with radius, you can do that, but this is what I use. I always say that, so it's pi times 100, because 10 squared is 100 divided by 4. Area equals 314 divided by 4. 100 pi divided by 4. Well, it's going to be 25 pi, right? Which is 78.5 millimeters squared. We go together like megapascals and millimeters squared. Support cable must not exceed more than 0.5 millimeters when placed under maximum tensile force. Calculate the maximum allowable length. So they told us that the change in length, which is delta L, which better written as E, is 0.5 millimeters. And with that, we now want to find L. So we've said before that to find L, we're going to take E, we're going to multiply both sides by EA, and we're going to divide by F equals L. So I'll write it just to this side. Now, always check with FLeA questions that there isn't some reference to factor of safety. That's definitely a thing. They've used the letter P instead of F. I've written F there because FLeA sounds better than plea. So L equals, our Young's modulus of elasticity is 180 times 10 to the 3 times our extension, which is 0.5. Just checking it's 0.5, not 0.05. Yep. Multiplied by area, which is 78.5. Let me know if I've done anything wrong. And we're dividing all that by 6 times 10 to the 3. I've changed that to 6 times 10 to the 3 because I want to cancel out. And so what I'm going to do is I'm going to cancel out that and that. Our answer, because we've used grease units, length is in millimeters. So I've got 180 times 0.5 times 78.5 divided by 6 equals 1177.5. So L equals 1177.5 millimeters. Someone could check if they wanted to look for the 2002 answers. I probably should get people having the answers ready to go before we start, but so I will leave that for the moment, and we're going to go into our next question. So we're going to go into we're jumping around a little bit in our order, and that's just based on what I have on my pictures. Okay, so I'm now going to do the 2011 paper, question 18, and it says, can you read?
Copper wires 8 meters in length.
Okay, so L0 equals 8 meters.
In length has a cross-sectional area of 0.5 millimeters squared.
Area is 0.5 millimeters squared. Okay, so we don't need to convert from diameter. That's a really common thing. Yep.
Given that Young's modulus for copper is 111 gigapascal, 111 GPa.
Yep.
Calculate the extension in the wire if it experiences a tensile force of 300 newtons.
Okay. So we're looking for, we have everything except, what is the told us the extension? Oh, no, they've told us the force, F. F equals 300 newtons. Okay, so that's pretty easy. We're just taking E, remember we can say that the E's can be swapped, FL over EA, and what we're going to have here is F is 300, L is, I'm going to write as 8 times 10 to the 3, divided by E, which is 111 times 10 to the 3, times area, which is 0.5. We can cross out, bad for the marker, but good for our calculator. And answer is going to be in millimeters. 300 times 8 divided by 111. Now, because I'm worried, because it's a denominator, I'm going to put that in brackets just in case I have a problem. I could just divide, I'm not going to do that maths. So I'm putting it in brackets. I get an answer of 43.6 millimeters. It's a big extension. I'm not sure that's right if you guys have checked the answers, but that's what we're gonna write. Okay. Going to move on to the next question. We're at 2009. I don't know what the question's from, but we're just going to say 2009. It's going to be hard to check our answer on this one. People love to be wrong on the internet. Calculate the minimum diameter of a bolt that will support a tensile load of this with a maximum allowable stress of that. This is pretty simple for us. Okay, so what we've got here is we want to find the diameter is unknown. The diameter is unknown. The force, or the tensile load, is 79. 76.35 times 10 to the 3 newtons, and the allowable stress equals 300 megapascals. Stress equals 300 megapascals. They're asking for a diameter. So what we're going to do here, the challenge here is being able to convert from diameter into area. So what we can do is we can find that, in this case, all we need to use is stress equals force over area. Stress equals force over area. So that means that our area is going to equal force divided by stress, which is going to equal 76.35 divided by 300. How many marks is this? 2? Okay. 76.35 divided by 300 gives us an area of 0.2545. Now, for me, just because if I was feeling a little bit sheepish, I'd just say, hey, let me just check that my stress equals force over area. So if I take my force, they've told us the force was that, 36.5 divided by area, which we said was divided by 0.25, I get 300. That's just a way of doing a check, just to make sure I haven't got my algebra wrong. Normally I don't do that, but sometimes, if I don't have a good intuition of if that number seems plausible, that's a way that you can check. Now that's in millimeters squared. That's not a diameter. So what we now need to do is we need to say that area equals pi d squared on 4. So that means if we want to find diameter, we can say diameter squared equals area 4 area divided by pi, and that means that d is going to equal the square root of 4 area divided by pi.
Times 10 to the 3.
Excellent. Thank you very much for that. I have made a mistake, and my students who are very clever, they have figured out for me that I have made a mistake, which is that...
Makes more sense.
Yeah. Good catch. I appreciate that. I'm always happy to be told that I'm doing things wrong, especially because it means I don't have to re-record this whole video. So multiplying that number by 4, dividing that number by pi, taking the square root of that answer gives me 18 millimeters squared. 18 millimeters diameter.
That's correct. I checked it.
Excellent. I'm really glad you did that. Thank you very much. Okay, so that was our 2009 question. What do you know what question number it is?
It is question 14.
Question 14, A or B?
B,
I. Excellent. Thank you very much. I'm really glad that you did that. Okay, the next one, 2012. Now, the only thing I will say is, if I hadn't multiplied that by 1,000, if the students hadn't caught that error, I would have got an answer that was 0.00018 millimeters squared. And that would probably have keyed me into the fact that maybe this was not a reasonable value for the diameter of a wire. So that's like, if you're getting a value that says that the wire is less than 0.1 millimeters in diameter, you have to think that's very, very thin. So sometimes it can be useful to allow some logic and say, hey, look, I tried, I can't find my error, that's okay. But if you find an answer that seems unreasonable, what you should do is put it through a second time. And that's where, when I had that area that was so small, I was concerned. And you saw that I typed it in the calculator because there was something flashing there that's saying, well, I couldn't see the error, but I'm going to say I'm on camera. Being on camera makes me a little bit nervous. Okay. Excuses. Okay. So, 2012, question 12, A, and then we're looking like we've got 2 different questions here. Okay. Determine the Young's modulus. So we've got a whole bunch of data for this question. We're told that the original cross-sectional area, which I'm going to write as A0, equals 40 millimeters squared. And we have gauge length, so that's the original length, equals 120. They sometimes use that term for original length. We have load at the proportional limit. So if, and I'm going to write y for yield, even though it's proportional limit, that's close enough, times 10 to the 3 newtons. Hopefully I won't forget that this time. Newton extension at proportional length, so this is delta L or E equals 0.19 millimeters. And then we have maximum load, so this is F max equals, this, I really could write that as F UTS, right, ultimate, something like that. But I'm going to keep it as F max rather than FU. Is 18 times 10 to the 3 newtons. And the extension at maximum load, so this is E max equals 4.9. Okay, in terms of the Young's modulus, so Young's modulus is E equals FLeA. And what do we know here? Well, we're told that we're finding determine the Young's modulus for the structural steel. So the Young's modulus occurs at the proportional limit. That's the definition of what the proportional limit is. The proportional limit is where the gradient, or Young's modulus, ceases to be consistent. So that means the values we're going to use here are going to be the values of the proportional limit. So we're going to use Fy, right, L. In our case, we can use the original length, LO, divided by the extension at the proportional limit, which is EI. We didn't write EY, but we can write that now. And the area divided, the original area. That's reasonable. Okay, so what we're going to do here is we're going to say that we have 13 times 10 to the 3 times L, which is 120, divided by extension, which is 0.19 times area, which is 40. Okay, 13,000 times 120, all divided by brackets, 0.19 times 40, close brackets, equals 205 times 10 to the 3 megapascals, which equals 205 gigapascals. Okay, so that's I. For II. This question says, determine the ultimate tensile strength, UTS, in the structural steel. Okay, so strength or stress is sigma equals F over A. But in this case, what we're going to look at is we're going to take, are we finding the true strength or true stress, or are we finding the engineering stress? What would we imagine?
Engineering.
Engineering is the answer here. So that means that we're still going to use F maximum divided by A original. Yeah, if we were finding the true stress, that would be a different calculation. That's where we would use the area at failure, the area at, they didn't even give us the area at failure, so that's good. They've made life easier for us. Okay, so F max equals 18,000 newtons divided by an area of 40. 450, didn't even need to calculate. Excellent. Megapascals. That seems pretty reasonable. Steel, we say that steel typically has a yield strength of 300, but having a UTS of 450, totally reasonable for mild steel. So this is where some level of estimation can help us. I will go through some more questions on FLeA, hopefully in another video.